So we're going to work a little bit more on zero-dimensional data and thinking about how do we actually see numbers. I've got to turn this on. Right. So recall from last day, thinking about what is actually in a number. Okay? Well, we want to visualize that number. We want to present its content to the viewer. And that content could be just it's identifying a unique value. That's all that matters, that this value is distinguishable from another. Or it may be that this value is a little larger than that, or it's just larger ordered. Or maybe the difference in the size might be important. Or some magnitude that we have here, for example, that you can tell that the ratio of any two numbers is meaningful, so that you want to be able to capture that and express that. So something like heights of individuals, so it's a meaningful ratio scale. Unlike, for example, temperature, where there's no natural origin of the thing, so that ratios of temperature are not typically of any interest or of any meaning. So that's what's in a number. Those are the properties that we want to be able to capture and display. So thinking first just about identity. Well, last day we looked at these QR codes and these barcodes, and here are in fact 4 different numbers. And you can think about how easy is it to distinguish between those 4 numbers. Certainly they are distinguishable, and you can decode them, at least the barcodes, you know the rules for the barcodes, so you could decode those numbers. But it would be certainly much easier for a machine to be able to tell the difference between those numbers. Especially it's been set up so carefully that to know where the start and the end of this is, so whether I'm reading right to left or left to right, it can tell which is the orientation and tell what the middle is for the barcode. So if all I want to be able to tell is the difference, the identity of things, this is really handy when the data is categorical. And by categorical, we have lots and lots of examples. So just a binary variant, right? It's either heads or tails, like a coin toss, or it may have 3 different values, the state of health, well, ill, dead. Or it might be a real categorization like a mammal species, baboon, rat, dog, human, etc. Another binary, sex, male or female. Color, red, orange, yellow. Or person, the actual individual that we're looking at. So that might be people that are more easily identified by their name, Justin, Amir, Anna, etc. Okay? So any set of distinguishable visual representation will do in order to distinguish identity, as long as we can tell one individual from another. But some are better than others. So for example, we might look at some simple stick representations of individuals. And so I ask you here, how many L's do you see? They're just L's and T's. How many people see only one? Show of hands. 2? Few people see only 2. 3? Guys, I've got to be a little prouder of you. So more people see 3. 4? 5? So it's a little hard. I think there are in fact 4 of them there. And we've got not just that these 2 different representations look alike, but rather the orientation is sort of getting confounded. Right? We're using several things actually here to identify people. It's the position of the icon on the screen there, and the orientation maybe matters, maybe it doesn't matter. But certainly the letters L and T, identifying between them becomes very difficult, largely because of the orientation. And should point out again, back to your very human nature, there are neurons in your brain that fire when they see lines at this angle, other neurons for other angles. There seem to be neurons that are specialized in particular orientations of a line. So some of these may be getting confused with these 2 things here. They look a bit alike, perhaps. So just so you can see it on these 2 here that I'm talking about look a bit alike because the orientations are very similar, particularly if they're far away from each other. You might also think about just using shape. So you looking at different shapes, and you can identify The individuals by their shape, you can identify the categories. Those that have the same shape perhaps are from the same categories. They have the same value of that categorical variant. And some of these are pretty easy to detect, are the same. Things like the stars that are fairly regular, but they're different in size. Maybe that's meaningful. But the important thing is these are the same shape. These arrows are the same shape. It gets a little harder when it's more irregular. This shape and that shape are the same shape but different sizes. This shape and that shape are the same shape but different orientations and sizes. And maybe this shape is the same as the other two shapes, but maybe it's not because it's actually reflected. It's got just not the orientation size, but also a reflection in the plane. So it becomes difficult, but easier if we have regular shapes that we can recognize. Something that's often overlooked is just using placement. So if I have a categorical variable that has 3 values in this case, I just place the points that represent the individuals that have that in different boxes on the page, on the screen. So I could just place them in a different location spatially, and also then within that box maybe encode some other variant by the position within that box. So the category, I can just place it different places on the screen. Sometimes you see that language sort of a facet. Think about it, I put this facet here or that facet there, etc. Might also use words. So we have a great familiarity with the alphabet and with the English language here, so we could use words to identify different categories. So if it says blue in 2 places, that's the same value. There again could be some confounding here, particularly the blue that is actually drawn in red color. So the confounding the red, sometimes going over that quickly you would say red rather than blue. You might recognize the color before the word itself. So in each of these cases you have to be careful. There's going to be some confounding with some other feature of the display. So something that we're really good at are faces. You guys don't all look alike to me. I can recognize you. You all look different. And we're all very, very good at recognizing faces. And these faces are lots of people that you might know here, people that you don't know. Sometimes straight on is fine, but even a slight orientation, we could recognize a different face, the same face rather. Okay, so we can tell faces apart. We can tell who's familiar and who is not familiar. So we might identify with any category a particular face. And there's reason that we're good at that. So evolutionary, there's all kinds of reasons that we need to be able to recognize predators, right? Things that have binary binocular vision looking at you are typically predators. You want to be able to tell those right away. So you need to be able to recognize faces in lots of different situations. But as humans, principally in a social situation, so you want to know friend from foe. You want to be able to empathize, understand what's going on in that other person's mind. Sort of, are they upset? Are they friendly? Are they angry? Etc. And you find again that we have neurons that are sort of dedicated to faces. So if we look at these, are actually measurings of a firing rate of a particular cell. When the subject is presented with the face at the top here, which is fairly recognizable as a face, you get lots of firing in that cell, lots of activity, and we take away some of the information about the face, the eyes, the nose there, and we still get some firing. And if we get even a really bad grade school picture of a face, that cell still fires. You start giving it random noise and it's not firing nearly as often. So we have things that are coded for faces. So faces are pretty handy, and we'll probably recognize them in any orientation, and even upside down, sideways, we'll still recognize it as a face. Well, you might recognize this face. Anybody know who this is? It's who? George Obama. Not really. It's actually Barack Hussein Bush. So you notice this is a merge of these two faces. And one of the interesting things here is that you recognize each of the components there. You recognize that George Bush is in there somehow, Barack Obama's in there somehow. Putting them together, actually, it's probably a better looking guy than either one of them, right? And that's interesting as well. I mean, researchers have found that we tend to find most attractive average sorts of faces. So if we were to take all of your faces here and average them in sort of this way, most people would agree that that would be a fairly attractive person. So we're wired in strange ways. So, but we can also recognize this face, as I said, for any orientation. So for example, if I turn that upside down, you still recognize that as the Bush-Obama combination, right? Any orientation will still do. So I start looking at this different, you still recognize that it's still a face. Move it around, still a face. Move it around, you recognize that. Things are going a bit strange. I haven't changed the image, I've just rotated it. So this is not the same image as we saw before. And I'll just go back there just to convince you. If you look upside down, now turn your head, you'll see that I haven't pulled any, there's no trickery here. So all I've done is I've taken the original image, cut out his eyes and mouth, and turned them upside down. But you're quite comfortable with them in the other place because the mouth and the eyes are very important to us, right? To recognize those features, the mouth and the eyes. And so you were happy with it in the upside down position on the left because the mouth and the eyes are in the right way around for the way we normally see them. So an important lesson here is actually you've constructed that image. Okay, you're not like this camera that's recording things. There's a lot of interpretation that's going on in your brain to figure out what it is that I'm seeing. And that what's happening in the brain, that's all derived from our evolutionary path. What was it important to us as a species to be able to do easily? So recognizing eyes and mouths is pretty important. Turning it and recognizing also that that's probably not somebody you want to mate with. Oh, maybe you do. So what you see is a mental construction. And unfortunately, that means we see these things everywhere. We have a tendency to construct faces, and you've seen this in the news, typically in some rag that's producing information. So we have, years ago, this face on Mars. What's going on there? Must be some sort of statue. And it's really entirely due to the resolution of the picture that's taken there, and that we will construct faces out of anything, because it's important for us to recognize faces. Now on the right, this was a grilled cheese sandwich that this lady claimed. I think that's supposed to be what's her name? Mary, right? The Virgin Mary has appeared on the grilled cheese sandwich. I look at it, it looks a little more like Marlene Dietrich to me. But this woman sold this as some miracle that had happened, that Mary had appeared on the sandwich, so sold it on eBay for a considerable amount of money. So we construct these images, whether they're there or not. And how do we do that? Well, our visual system is quite complex. In particular, it's complex mainly what's happening in your brain. But a lot of the stuff, a lot of your brain actually extends into your eyes. The neurons appear in the eyes. And what's really handy in identifying identity is just to use color, because we can recognize different colors. So I want to think just briefly about how your eye is constructed and how we see colors. So when we look at this as your eyeball cut through, sliced through on side, so that what's happening is the light comes in here through this transparent cornea that's covering it, through an opening whose the size of the opening is determined by your iris, that's your pupil. It goes through a clear lens, which gets less clear as people get older. That's why they have cataracts. And you change the shape of that lens to focus the image on the back of your eye. Now that image is going to be upside down, actually, on the back of your eye, where it appears, just because of the nature of lenses. And the focal point of the lens is this point called the fovea. So this is coming through here, and we have to have light detectors on the back of your eye, the back of your eye being the retina. So here's a slice of a retina. So light's coming in from the left and hitting the back of the eye. This is all your retina, all this blood tissue and everything else. And what's happening is the light's coming through, it has to get through all of these blood veins and other things back to the light detectors are really at the back of the eye. Not only at the back of the eye, they're pointing backwards. This is not intelligent design, right? This is dumb design if it were design. But it's something that evolves naturally. So the photoreceptors are at the back of the eye pointing the wrong way, and there are two types of photoreceptors. There are so-called rods because of their shape, and cones because of their shape, these sort of carrot-shaped things. And roughly speaking, the cones detect the color, and the rods, lightness and darkness. And if you look at the back of your eye, you can see that they're not distributed evenly. So this curve here, this solid curve, well, you see there's a blind spot there. That's where this optic nerve exits. It's gathering up all of the wires, so to speak, all the neurons, and pulling them back into roughly the middle of the brain. So there are no photoreceptors here. So that's why you have a blind spot. So the rods are distributed across the whole of the retina, more and more on the outside, less in the middle at the fovea where the focal point, but the cones are concentrated around the focal point. So those are all your color receptors. Yes, question? Oh, okay. So it's not an even distribution, and these things are mixed, so you'll see lots of cones out on the edge, but not nearly as many as there are rods. And there are tons and tons of these receptors, roughly 130 million photoreceptors in the back of your eye. Okay? And they're connected to many, many more neural cells, also in the back of the eye, before they finally reach the brain. So, color. So we're pretty good at color, so we're going to look at a good way to distinguish categories is by color. And what we traditionally think of as color, the thing distinguishes red, green, blue, etc., that's the hue. Okay, so we're looking at changing in hue as a way of encoding a category. So we can tell that things are certain the same category, but some are kind of close, but maybe not the same. As the things get closer in hue, it's maybe a little harder to distinguish. So these work best using a hue if you've got few categories. The more categories you have, the more hues you have to have, the harder it is to tell a difference between some of them. Okay? And then we have this problem that some of us are colorblind. So this is important to take into consideration when you're producing a visualization, say for the web or anywhere else, that you think about the audience, that many folks are colorblind. Roughly about 1 in 12 men and about 1 in 200 women, okay, are colorblind. So, question, how many people can read this number on the left? Hands up high. Back corner, you can't read this, or you're watching a movie? Not you, the guy in the very back. Okay, middle number. Okay, who cannot read the middle number? It's okay. On the right, you can see a path. How many people cannot find a path from one X to the other X through that? Anyone not see the path? Yeah, you can't see the path? There should be some small fraction of you that cannot see these. You cannot see it? Okay. I don't think it's the glasses. So colorblindness is a problem. And again, we're looking at how the back of the eye works. And as I said before, the rods are incredibly sensitive. So they can detect apparently down to a single photon. And that's sort of where you get what you're using in nighttime. That's why the night seems kind of black and white. Right? The color cones are not picking those up. So the rods just detect black and white. In cones, we have 3 different types of cones, roughly corresponding to a red cone, a green cone, and a blue cone. And it's sort of that range of the electromagnetic spectrum that they react to, that they're sensitive to. And together, the three cones can allow us to distinguish the colors of different objects, everything that we see. And it's not surprising if you look at an RGB display, that are red, green, blue, that you can construct pretty much any color from on your terminal display. And what they're sensitive to depends upon, so the wavelength is on the bottom left, so short wavelength on the left, long wavelength on the right. So we're looking at the blues, the purples, the indigos down here, and the yellow, red up on this side. And so the rods are sort of across this thing, can detect, will fire for light kind of in this range. And then these short cones, roughly the blue cones, if you get a color in here, it fires the most. Okay. Color in here, it fires about that height, etc. The long one here, the red one, it's going to fire most at this area, which is curiously not red, right? And fire very little for any light that hits it on this part of the spectrum. And the green cone, the medium one, firing most for this part of the spectrum, and less so as it drops off. So your red cone is not firing only for red, the green cone is not firing only for green, but rather they're all firing at what light hits it, just at different intensity depending upon the wavelength of the light. With those three pieces, knowing what the intensity is on the cones here, etc., where you are, you can figure out where you are in that spectrum with those three things. So that's what's happening. So that I can distinguish reds over here because these cones are firing a lot more and the greens are not firing very much at all. So that's what tells me it's red. Okay? So it's the differences in the signals. Evolutionarily, I mean, all apes and old world monkeys, for example, have three color cones like we do. New World, a lot of them have only two color cones. And if you have a deficiency in any of these cones, it affects the colors that you see. Other animals have lots of different color receptors and have different sorts of vision. So if I'm looking at color blindness, and if you've got a deficiency in the red cone that it's giving you a weak signal, the normal vision is on the left, but somebody with that red deficiency, protanopia, will see is something like on the right. Okay. Does anybody here not see a difference between those two pictures? It's okay if you don't. If you've got a green deficiency, that's what you see, which doesn't look that different from the red deficiency. And that's because those two curves are very close to each other. If you've got either of those deficiencies, you're still picking up blue and yellow very easily. If you have blue deficiency, that's what it looks like. So you have to keep in mind when you're constructing a graphic that people viewing it may be deficient in some of these ways. And I've given you a simulator here. If you click on that link, you'll find something that you can look at your image and see what it looks like to people with various color blindness. Some people, by the way, have none of their cones are working, so all they're seeing is a black and white world. There's an interesting TED Talk if you want to look at some fellow that discovered that he was achromatic, meaning he cannot see any colors, and had a device built so that the color, so it would read color, an optical device read color, and translate that into sound into an implant. Here, and he wore that for several years. They're still wearing it, I guess. And so he hears color as opposed to seeing it. So if I upload the graphic in the top left corner, that's a normal vision. That's what that simple graphic looks like, going through the colors of the rainbow, from red, orange, yellow down to indigo, violet. In the various deficiencies, you can see how it wipes out certain colors, certain differences. So the red and the green look kind of alike, but they're slightly different in what they wipe out, and the blue deficiency looks quite different. So if you think you're presenting this and somebody's only seeing this, well, they're not seeing too much distinction between these middle groups, for example. So again, for a visualization, it's really essential that you check this against a colorblind system. Okay, other ways you might use colors. I mean, if you look at Excel graphics, you'll find that there's all kinds of ways of producing really, really bad graphics very easily. And one of them is to introduce a gradient all the time. And so we have this gradient that's the same hue, but the saturation changes depending on which circle I'm looking at. And I can identify categories, two categories here, by whether the gradient is bright at the top or bright at the bottom. What else do you notice about this? Sort of a 3D effect. This circle here, is it pointing in or out? In. So that looks like it's concave. This looks like it's convex, right? It's popping out. The reason for this is that you naturally assume, again for good evolutionary reasons, that light comes from the top, because that's where the sun is and the moon, right? So you naturally assume that, so that you're going to make that sort of 3D construction, and it is entirely a mental construct that you've got 3D there just by on the gradient itself. So here's an example of that. This is a wood carving, and you can see that it's an elk or a deer of some sort carved out, and the deer is standing out. These bits back here are cut away. You can see a bit of the chisel there that's used, and the deer is popped out with all of the leaves. If I turn that upside down, that's the same picture, right? And now it looks like the deer was cut out, and these things are the things that are sticking out. It's entirely constructed by your brain. The only thing that's different is I've turned it upside down. Other features. Well, you might think about using saturation here. This is just grayscale to distinguish categories. And one of the nice things about this saturation, it also kind of gives an ordering from light to dark. Okay, so it's a great way to introduce different categories, as long as there are a few of them, and in inducing kind of an ordering there. Now you may notice that these pictures, these bars, look like they get light on the right, dark on the left, light on the right, dark on, dark on the left, light on the right, dark on the left, light on the right, sort of this scalloping kind of effect. Do you see that? Does it look kind of like it's doing that? That's called a Mach effect. And that's not there, that's entirely, again, constructed by your visual system. Because you're trying to introduce, however, we're not sure exactly how physically, but there are lots of suggestions of how that might happen. You're trying to introduce this contrast at the border. So you're sort of lightening up one side, darkening another side, and now you've got this scalloping effect, which is not really there. Distinguishing categories through colors can be severely affected by the surrounding color. For example, if we're looking at these circles here on gray background, varying gray backgrounds, the circle in the center is optically identical. It's the same gray scale. Okay, so nothing's different. So if you were trying to encode a value or a category based on that gray, well, if it was set on different backgrounds, you might mistake the category, the identity. And that works with color too. So again, this rectangle here, the center rectangle is identical red color or blue. Okay, so the color is going to be affected by the background. You're going to be doing some processing, introducing that contrast and making these two blue rectangles look quite different from each other. Okay, gets more complicated. Your brain is so weird and wonderful, and again from your evolutionary path, that you actually construct colors. There is no color. There are wavelengths of light, but the colors that we see are entirely in your head, constructed. So, for example, you have to trust me. You can do this when you look at the slides at home, and cover it with a piece of paper that there's no trickery involved here. But those two rectangles or diamonds are optically identical gray. Okay, I'm going to start revealing some of the picture. It's going to be a checkerboard, which these are two checkers on, squares on. So as I reveal it, so first just labeling them, A and B, so you can follow which is which. And I start revealing some of this picture. Those grays have not changed. This is still the same gray as that gray. Nothing has changed. I'm just revealing some things. Okay, it's more and more of the checkerboard. The A square and the B square are optically identical grays. If you put a meter on it, it's exactly the same gray. What's going on? Well, the B is in shadow. So somehow your brain's saying, to see that, to make that sort of, this color constantly the same sort of thing in shadow, I want to lighten that up a little bit. But that's the same gray. So color is a construct in your head. Okay? And we can see this if I add a gray stripe, that now looks like a gradient, doesn't it? That's actually the identical rectangle, same gray, I've just placed it on top of the two squares. Here's a ladder comparing all of these squares. It makes it a little easier to see that it's the same color gray because we've kind of matched them up. But the only difference between these two images is that this ladder, these two parallel bars are placed on top. Okay? So color's kind of treacherous. Okay? If I place an orange circle, and you have to trust me that I just cut and paste this orange circle on top of two different places, that's optically the identical circle. Just copy and paste. Looks a lot brighter when it's in the shadow. And theories are the sort of color constancy that we want to be able to recognize the fruit, whether it's in shade of the trees or it's out in the open sunshine. We want to recognize the same thing. So we tend to lighten these things up to try and get the color to be constant across these different things. It assumes that it's in shadow, and so you have to lighten it up a bit to get it more nearly the correct color. Okay? So color's very, very important, but very, very tricky. So there are the two things when I take away the image. And again, zoomed in, the bottom one looks brighter. Okay, so that's categories, and colors are pretty good for categories if there are a few of them. Want to think about magnitude of a number. How do I represent that? And so there are lots of reasons for doing that. One is to discriminate between the numbers, the identity, to rank them, to order them, but then to judge the relative size. So for some purposes it might be enough to just distinguish smaller than, much smaller than, about the same, larger than, sort of rough, maybe even just a partial order. For other applications, we actually want to know the difference in the size, difference in the magnitude of those two numbers that are encoded. So our objective is to produce a visual representation that actually encodes the numbers and allows us to retrieve to some level of accuracy the magnitude that has been encoded. And so things that we might use here for categorical values are just the color, the hue, saturation, etc., the shape, and where the size, and the visual location. So an order by color. We did this with the grayscale before. We can order this just with the lightness, sort of changing this thing. In R, there's a color palettes.r on the course website, or I'll put it up there. And looking from, let's say high values to low values, high values to low values or vice versa, but it's clearly got an ordering. And that works, again, pretty well provided there aren't too many of the categories. So these are called palettes that I want to go on, some palettes that allow me to distinguish categories by color. And again, introduce a nice order. Here's a so-called divergent palette, where you're only using two different hues and the saturation of two different hues and looking at an origin in the center. So you might think of this examples, you'd see this in, whether it's above or below sea level or above or below zero temperature, etc. But you've got a natural origin that you want to identify and increasing values positively, increasing values negatively, or vice versa. So a divergent palette can be very handy, again, provided there aren't too many numbers. But as it says, effectively, you can double the number of values that can be ordered. So palettes are pretty good. So changing saturation or lightness, I can see from low values to high values on any one of these hues, a grayscale or blue, anything that you like. Some folks like to use changing hue as well. And so here I'm going from a red to a blue, sort of merging down into the kind of purple in the middle, up a yellow to a red. So these are nice natural things that switch into each other. You know from your own work, working with, why is Google bothering me? Working with your own mixing of paints or filters of lenses, etc. And what's really important, again, you think back to our cones, which cones are more sensitive, we actually get oppositional colors. So red and green are opposing colors. Blue and yellow are opposing colors. So it's nice to think about how well might either of these do for various kinds of color blindness, for example.
All right, I'm going to pick up from where we left off before that technical glitch. We're looking at saturation and representing magnitude via saturation or lightness or hue. So it's of interest to think about, well, if we encode a number via saturation or lightness or whatever visual means, how do we actually decode that? And to get some sense of how we decode that, we need to look at psychophysical studies. In psychophysical studies, particularly with respect to color here, looking at Joseph Albers' Longo's 1963, observed that if we increase, say, saturation or darkness or lightness here at a linear rate, so we know that that's changing, the stimulus, the physical stimulus that's coming in is changing at a linear rate, so this is 5 times that. And what we actually perceive that magnitude to be, that is decoding, so this is the encoding. What we perceive that to be as the decoding is not really on that linear scale anymore. That is, this high end, we don't perceive that to be 5 times that, but it's something rather smaller. So this sort of attenuates here as we increase this physical stimulus, our perceived, our perception of the magnitude of that stimulus is not really increasing at the same level as the magnitude itself. So in our decoding, it's a little under what it should be. That means that if I want to actually perceive a linear increase like this for the magnitude, that rather than having a linear encoding, I need something that's sort of superlinear, moving up here much more quickly above linear. To perceive something that's 5 times that size, I may have to have it many, many times the size in order to it to appear to be 5 times that size for me. Okay? So we have to think about that. Well, what's the effect there when we look at different kinds of encoding? So if we think about encoding magnitude by area, so what is the area of this shape? Assuming this shape has area 1, let's say, what is the area of this shape? What is the area of this shape? Maybe we have a better sense of what the area of this shape is compared to that one for area 1. So it seems to work a little better with regular shapes that are all the same size as opposed to irregular shapes. Comparing one to another may be a little harder to compare. But particularly nice, so this one that can fit inside that, we can think about how many times does it go inside that. Or these, at least we could order them all to the regular shape. So think about encoding the value as an area, the area of some shape, probably something a little simpler like a circle or a triangle, and how would we decode that? Another way to encode magnitude visually is just by the length of something. So this line is encoding a particular number, this line is encoding a slightly smaller number, and perhaps this line here, the length of that line is encoding the number 1. If that's 1, length 1, what is this value, right? Can we decode what that value is knowing that that's 1? And so that's the challenge, is encoding the numbers in some line length or length of some object. Can we decode what its actual value is? Related to line is thinking about the position rather than just putting a line here. Just mark where the end of the line would be, the position of this point along this scale. So there's the magnitude encoded there. The magnitude of this one is encoded there, of that one there, this one here. So encoding that way and knowing that, say, this one is 1, what are the values of these other ones? So that would be the decoding. Certainly we can, there's also the thing of, can you order them? Ordering is probably a little easier than actually getting the magnitude, but we're interested in getting the magnitude out here. Alternatively, to the length, lines also appear on the display. They've got some sort of slope. So we think about when we maybe have some better sense of what a slope is, of those of us that have got some experience with Cartesian coordinates anyway, that this may be close to a slope of 1. This looks like it's greater than 1. This looks like it's greater still than 1. And if it's going the other way, right, it would be a negative slope. And a zero slope would be flat. So we know that we've got some signed magnitude here, which is pretty handy. The question is then, can we decode it? So given that, let's say this guy is 1, right? What is this value? Or what is this value? Is this value larger than that value? Can we order them? And can we extract the magnitude? Another possibility is knowing something about angles. So we can certainly order angles here, at least those that are far apart from each other. This angle is less than that angle, is less than that angle, is less than that angle. These ones are a little hard to distinguish, maybe this one and that one, the closer they are to each other. But can I actually get the value out of it? Certainly right angles will be easy to tell the values, but some other ones, what is that actual value? And angles appear in all kinds of graphics of encoding values. You can think, for example, pie charts. Partially, at least, encode the number as that angle. What's popular amongst things like commercial graphics, because they some have some sort of aesthetic appeal as opposed to some value in encoding and decoding, is look at the volume. So we encode a single number as the volume of this. So rather than the height of the cylinder, think of the volume of that cylinder, and that's the size of the number, or the size of this box. So given a unit volume in this situation, can you extract the magnitude from the volume of the object displayed? So to get some sense of this, we have to look at actual human experimentation to see what works and what doesn't work. And so we go to psychophysical studies for this. And psychophysical researchers have discovered through lots of human experimentation things that are common across senses and across various sorts of stimuli, and that they effectively empirically determine laws about human perception. And so that perception again could be to sound or sight, and we're interested in sight here. And the notion again is, if I give a physical stimulus that I can actually measure, the area, the length, etc., and then I ask the person what is the actual value associated with that, can I? That's the perception. That's their perception of the value. So the encoding is the physical stimulus itself that's under our control, and the decoding is the person's perception. And to make things just another sense, you might think about holding up a weight, in your hand and changing that weight, and what do you perceive the change in the weight to be, or how much heavier is the object, etc. So we're going to look at a number of laws here. The first law is Weber's law, the earliest one that's discovered, or Weber-Fechner law. And the notion here is that x is the physical magnitude of the stimulus. So that's our encoding, right? We're encoding that as the length of a line, or the angle, or the area, etc. And I want to think about what's the smallest piece that I can add to x. How much longer can I make that line? How much bigger can I make that area, so that I actually perceive it to be larger? And so you think about it, it's a just noticeable difference, right? I can just notice this difference here. Or if you like, since I'm not going to notice the difference all the time, or alternatively, over many people, not everybody's going to recognize that. Think about the probability that you're going to recognize that. So this is going to be perceived to be larger with some probability p. At some point, if WP of x is large enough, it's going to be probability 1. But we want to think about smaller values. Well, Weber's law, this is observed empirically, suggests that WP is actually just proportional to x. So whatever the stimulus is, the bit that you have to add is something proportional to that, the size of x. So it depends on x. So if we look at the ratio, for example, of the stimulus plus that amount that we add to it, to the original stimulus, so the bit that we're adding, you see that all that matters here is that proportionality constant. And that kind of makes sense if we think about lines, for example, that a 0.5 centimeter addition to a 2 centimeter line is much easier to detect than a 0.5 centimeter addition to a 20 centimeter line. The first is a 25% increase. The second is a 2.5% increase. So the proportionality constant is different in these two cases. And where it's larger, it's easier to detect. And we could see how that might be used to explain our perception in encoding data as lengths, for example. So we look at the height of these two bars. Which one of these rectangles is longer in this direction? And you look at that for a bit, and you think about, it's probably B is what I perceive to be the longer rectangle. But it's not quite so easy. It's not immediately obvious. You have to do some careful comparison, imagining that B is down, the bottom rectangles are side by side, and then if I were to move this, am I moving this at the same angle as I'm moving that? All right, that angle looks steeper than that angle does. But it's not that easy. And one of the reasons is that this difference, the difference in the heights, according to Weber's law, the height of B is only a small, the difference in B and A is only a small proportion of A itself, of the length of the height of A. So that's what makes it hard. But it's just a fix to make that easier, is to put a little frame around it. So if I put this box around both, and that box is the same height, so you can see that's the same height. If that box is the same around each, then it's immediately obvious that B is got a longer rectangle than is A, the black part. And why is that? Well, the reason is that we're no longer comparing these black components, but rather these white components. And if you look at this difference here, the height of this one minus the height of that one, that difference is a huge proportion of this one. So it looks like effectively a little more than doubling that thing. That's why it's so easy to tell the difference. And Weber's law suggests that as to why that's happening. So that means it's probably not a bad idea to have the lines sort of boxed in, so you can always see these things almost like thermometers, that you can always see either compare the black side or the white side, and one or the other will be easier to detect. Okay. Second law is rather than looking at comparing the just noticeable difference that we can perceive, think about actually decoding the value of the stimulus. So we encode the datum through some stimulus, the magnitude of that stimulus, the area, the line length, etc. And then we say, what is the actual value? And experimental evidence says that across a wide variety of stimuli and people, that the perception seems to be some power of the input stimulus. So if we're encoding it with X, our perception seems to be some power of X, beta. So what is that power? Well, we determine what that power is for different stimuli experimentally. So looking at encoding the number via length, presenting the numbers as lengths, this beta coefficient seems to be between 0.9 and 1.1, which is where we'd like it to be. We'd like that beta to be 1, because if beta is 1, then we're actually going to perceive something that's just constant proportional to the actual stimulus. So that's ideal. For area, however, it's something less than 1, which means we're going to, if we give the area here, if we encode it as area, what we're going to perceive is something a little smaller. In volume, it seems to be slightly smaller again. So there's some disruption here of the encoding. At least the decoding is not going to get us what we want. That suggests two things. One is that it may be better to encode the magnitude via length than via area. Better to encode it via area than via volume. And alternatively, it suggests that, if you really want to get this encoding, what you need to do is, rather than encode the stimulus as X, encode it as X to the 1 over beta. So if we had, say, 3/4, 0.75 here for beta for area, so rather than encode the area as X, encode it as X to the 1 over beta, or X to the 4/3, and then we may perceive this more closely to be X. Get a sense of what the actual effect is. Think about comparing two areas, A and B, and let's say its beta is 0.7. And according to Stevens' law, the ratio that we encode is A to B, but what we perceive is A to B to some power 0.7, to our beta power. So if A was 2, 4, 8, if the areas were 2, 4, or 8, we can imagine something, the small area to the 4, something that's half the size. Rather than appearing to as half the size, it's 60% of the size. Right? So the smaller areas appear a little larger. Conversely, larger areas, rather than being twice the size, it's only 60% larger. Okay, so small areas appear to be larger in comparison. Large areas appear to be smaller, and of course, it's going to be worse for volumes. So again, it suggests this ordering. The ordering is that you might prefer to use length over area over volume. But also, if we are going to use area or volume, and if we have a good sense of what the beta value is, we probably should encode it, the number by X to the 1 over beta, so that it comes out looking more like X.
So a bunch of other experiments have been done by Cleveland and McGill and others, looking at graphical perception. How well can we perceive what the actual value is that's been coded by different graphics? And a series of experiments, these folks looked at encoding the number as an angle or as an area, a circular or some sort of blob area, position where its position is along a common scale, position along identical but non-aligned scales, and length and slope. And so they looked at things like this, where we're looking at, for example, positions. Can you read off the value of each one of these guys according to the scale? Here, this is a common and aligned scale. If I was comparing these two groups, comparing this value to that value, or reading off one versus the other, and they're on common but non-aligned scales. So that's what we mean by common but non-aligned. So same scale, but just they're in different positions. And then we're looking at length here. So you're thinking about length of this block, A compared to B, what's the size of A versus B, etc., and comparing them across the A's, whether they'd be on a common scale here for the A's, but not so much for the B's. And also they think about looking at the rates of change you might have in a graph of that. That's really important, looking at the slope of a line. How well can you tell what that slope is? For other things, experiments that they've done, they looked at the positions, again, along a common and aligned scale, common but non-aligned, right? So they have different boxes here, and lengths here that are oriented straight up and down, or oriented on angle here, looking at the slopes, angles, area compared to area, what is the actual value area, whether it's nice something regular or just some irregular blob. So the results of these experiments produce the following ordering. And this is an ordering that I want you to keep in mind when we're looking at plots and constructing plots. So perhaps some of this is not so surprising, but the best ordering that we have that allows us to get back accurate values is going to be position along a common scale. So just plotting the point along a common scale, being able to read that off. Next, position along identical but non-aligned, followed by lengths, angle and slope sort of tied, then area, then volume. They also looked at color density, color saturation, that's way down there, and color hue. So as we might expect from what we've seen before, that's going to be the least valuable way of encoding the number in a way that we can decode it easily. But of course, this is all experimental research. There hasn't been much done in this in the time since then, but that's the order that we're looking at. You can also think about how this works for comparing angles, for example, what are these slopes of these lines. So we're looking at the ratio of the slope of BC to AC, right? Is that larger or smaller than it is here when I have this kind of aspect ratio than it is here? Okay, so the question is, how large is R, that ratio, in each of these three figures? So think about, is it largest in the center? All those in favor? Few in favor, largest here. It's the ratio of the slopes. Here. Well, it turns out they're all the same. So the ratio of the slopes are all identical, and it's a lot easier to tell in the center one what the ratio is of these slopes. And to a large extent, that's because things that are near 0 or 90 degrees, 0 or pi by 2 radians, right, are very difficult to tell. But we seem to be very good at telling things that are more on a 45-degree thing. And you can actually get some sort of mathematical justification for that if you think about the angle of a line segment and changing that line segment by a small amount delta theta. So the two slopes that you have of those two angles are going to be tan theta and tan theta plus delta theta. And if you look at the relative difference in those slopes, so the difference divided by the tan theta, for small delta theta, right, this looks like if I took this numerator divided by delta theta, it looks kind of like a derivative. So this thing is sort of like delta theta times tan prime of theta over tan theta. Right, so that's approximately equal to that. Gives us some sort of insight. A little work, that's delta theta times 2 over sine of 2 theta, just using a double angle formula there. And what that means is that this thing is going to blow up, right? If this is 0, if theta is 0, this thing's going to become infinite, right? So it's if it's near 90 degrees, it's going to be infinite. So this is all going to blow up, which means that if this gets very large, I'm not going to be able to really tell differences. You know, one delta theta is going to be about the same as another delta theta. However, this kind of thing is kind of minimized at theta equals pi over 4, which gives you some sort of hand-wavy mathematical justification for we seem to be very good at detecting pi by 4, and there's sort of so 45 degrees. So when we're looking at slopes, That's why the center thing, that aspect ratio, we can really detect 45-degree slopes a lot better than anything else and talk about their differences. So that's going to be essential when we talk about plotting things over time, let's say, and aspect ratios.